Yeah, I'm very happy to present this presentation on sort of towards industrial grade robot control in ROS. I was here last year talking about our initiatives of sort of reinvestigating the ROS driver environment around the UR robots, and in this presentation I'll look a bit at the results and also a bit looking ahead. What we, in many of the situations that we see UR robots nowadays is in factories like this, working in close proximity to humans or working as standalone industrial robots feeding machines, even behind safety curtains and so on. But we also see a growing movement against sort of people using our robots much more flexibly, being more creative in how they actually approach automation in factories. I think even today we've seen a lot of examples on how you can actually use collaborative robots for applications that aren't that difficult to do, but for many reasons haven't been automated, either in terms of logistics around the work cells or safety or many other reasons. And I think the work environment in the world in general is approaching a point where these sort of challenges must be tackled, right? That instead of trying to automate the very most difficult part that you can find in a factory, we actually go back and find the places where we actually can put in robots quite easily, perhaps with a bit of creativity, so you can move them around, you can anchor it up, you can get things working pretty fast. But we also see our robots being used in many other sort of scenarios, such as this is from the Olympics in Rio in 2016, where our robots were holding cameras and filming the big stages, where it was pretty difficult to get a guy up there. A lot of new TV studios actually don't have enough space to put in camera operators. So a lot of news broadcasts, for instance, is actually done with automated equipment, either by our robots, as in this case, or other systems that monitors, which really improves all the blue screen stuff that they can do. You see it every day, the quality of blue screen recordings that you can see. But in general, what we want to do, and I think the most important thing for Universal Robots, is also to empower people like you guys to do exactly what you want to do with research without spending your time on making the hardware work or making the interfaces work. So this is from AutoCAD. The AutoCAD people that use our robots to do a lot of research. So in general, we want to enable you guys to get all the research done that you guys want to do without really spending a lot of time on making the hardware do what it was supposed to do. So actually, I think this is one slide that I presented last year. So and why did we even go into looking at? There was a number of ROS drivers out there. So why did we need to change that? And I think the argument is pretty much the same thing as Matt Hansen presented yesterday. Why did Intel look into the navigation stack? That again, we had more than 200 variants of the different ROS drivers for the UR robots out there. And they had a lot of different benefits depending on what the use cases they were developed for. But I think the most common denominator was that none of them really had all of it. And they were also built upon some sort of internal APIs that weren't really that stable for changing, especially not in the way that it was implemented. So there's a lot of stuff that we can improve, just cleaning up the implementation and getting all the new features in. Performance and so on, especially on our new E-series, wasn't that great either. So we were happy that last year we got a grant from the ROS in, so we actually started a project together with FZI to do this. And in general, our goals was to make a driver that was ease of use. So you can really do plug and play control with a UR robot for any sort of research task you want to do. Right? In the end, that's what our robots are all about. We want to make sure that you can focus on doing the stuff that you do and not sort of spending all your time on getting the hardware to work. We want to make sure that we can sort of fully utilize all the features that we have on the robot. And we want it to be at least as industrial grade as the sort of current practice of ROS is. What is the next level there? I'll get back to that. And we want to build it sort of on stable versioned APIs so that it won't break all the time, so we can actually push updates to the robot without all of you guys having to spend time on fixing that. And put it into our testing regime again as well, so we actually will know if we break something. So, and keep it open source as well. So in June 1st this summer, we launched the beta program, and actually I announced the beta program here at this conference last year. And sort of as a participation for that, we got more than 73 partners from 12 countries that actually took part in this beta program. Helped us testing the driver, maturing it, giving us feedback. So we ran a beta round of about 3 months. And I think quite interesting, if you look at the profile of who actually joined the beta program, then we had 13 large industrial partners, mostly sort of corporate research departments in the different partners. Then we had like 16 SMEs and startups. I think around 3 startups and the rest SMEs up to the 500 employees, which I guess pretty much account for half. And then we have had the equal portion of research institutes and universities. And then there's a few undefined, so if you add them up, they don't fully add up. So I think it also shows a picture that ROS is really moving to a place where it's not only a university tool used, it is also tools used for industrial investigations, industrial research, and also in the perspective of actually commercialization. There was a pretty big portion of startups that had very commercial intent of sort of making this driver work, right? So I think it's an important thing that we keep in mind also when we move ahead, saying, okay, how do we make sure that we do not only make these drivers to making it easy to do sort of the research stuff and it should work today and tomorrow and we don't care if it works more than an hour at a time. We need to look about how do we get the quality and the performance up to a level where it really works in practice. Otherwise, we'll sort of still be doing the research for fun, right? So we publicly launched it in October 9th. It's hosted at the Universal Robots GitHub. I'll have the link in the end of my presentation. I think right now we're hovering around 20 unique clones daily, which I think is good. It's not exactly the same number as we had on the DDS clients we saw yesterday, so we'll probably have to work a bit on that. Maybe this conference will help. But I think we're quite happy about the spread still, that it's 150 to 200 unique clones weekly is still pretty good. Yeah. So next one, I'll try to show you a video that the team at FZI made that sort of highlights all the features that we put into the new driver, and after that I'll deep dive a bit into how we did it, why we thought it was important. So without further ado. Yeah, so as you can see, we really significantly improve a lot of performance features, but I think the most significant improvement is actually sort of the ease of use and how we actually streamline the whole integration chain through. So of course an important thing is to move to the stable industrial control interfaces. But having ROS as a part of a program really shifted the paradigm from you guys. If you had to use our robots in collaboration with ROS, you were sort of, with the previous drivers, forced to do all of the motion programming in ROS. And if your sort of research topic is motion programming, then that's a really good thing. But if your research topic is sort of more visual servoing, or it can be detection on computer vision or whatever machine learning you do, then having to do the whole teach-pendant integration in ROS may not be the thing that you really want to spend your time on. So now you can actually do a complete robot program, and then at any given time you can pass the control to ROS, make ROS control the robot as it wants, just for doing a small manipulation task or whatever, and you can actually transfer control back to the robot and let the whole program continue as it was defined. Which also again enables you guys to go a bit closer to the industry and making sure that sort of all the basic robot stuff that we spend a lot of time on making easy still works as people are used to and at the quality that you're used to. And in the end you can focus on the small part where you can really contribute. And I've seen that as a blocker sometimes to really getting the ecosystem in. Then we went to getting the factory calibration into ROS, the safety compliance, and also using some of the new features on the E-series. So if I deep dive a bit into it, I was around there just a second ago. So just having ROS as a part of the programming environment of the UR robot really makes the sort of industrialization and also maybe moving the path of commercialization of a lot of the technologies that you guys work with a lot easier. You can use the robotware and the teach-pendant of the robot where it makes sense, where people are used to using it. And then I think the good thing is also there was a lot of discussion around safety in a previous talk as well. It also ensures that we have a single point of control of the robot, right? So you can start the program from the robot, meaning that in the end, it is the guy with the teach pendant that somehow activates the execution of the program and at least ensures that we have a single point of control. We still support these, you can say the old paradigm of ROS control where you switch the robot into remote control mode. Again, leaving it up to you guys to ensure that it's safe around the robot, and then you can control the UR robot directly from ROS. But then you won't benefit of all the sort of teach-pendant integration and so on. So every UR robot that leaves our factory is individually calibrated for absolute accuracy, which is nice. It's actually a feature that people appreciate, but in the end have never been a part of ROS, which I guess is a pity, as that's probably some of the you as ROS community is probably some of the guys that really knows how to use this and probably could use this. So we made sure that came into ROS now, so there's a calibration tool where you actually extract the individual calibration of the robot into ROS, and we changed the structure so it actually matches a URDF file. So it took a bit of work. So as ROS is used as 6D transformations, I think our tech support gets this question touched around once per week on how do we go from DH parameters to any sort of other transform. So now we at least, together with SI, did it once and for all. So I think it's even if any of you guys are curious about that, we have a good reference implementation of that in the ROS driver. And because of a lot of the parallel structure of the kinematics of the UR robot, then sometimes the resulting DH transforms are surprising for some people. So we link it up to the serial number of the robot. So you may have multiple robots with individual calibrations. Of course, you don't want to be launching one ROS driver to a robot that has the wrong calibration or the calibration of another robot. So we link it up to a file with the serial number, so it should automatically load the right one when connecting to the robot. So safety compliance in general is an important thing to get working, and in a UR robot it's not just about keeping you guys safe when you're working with the robot, because that's always ensured, but the difficult part here is actually making the collaboration between ROS and our safety compliance system work seamlessly. So I think this graph shows the problem quite well. So in order to make the whole safety compliance challenge of a UR robot simple for any sort of unskilled programmer of robots, the robot is designed so that if you put any sort of safety limit in our safety system, it could be a maximum TCP speed, you can limit the momentum of the robot to sort of reduce the free air impact if you have a collision, or you can reduce sort of the clamping forces that it could give you in a potential clamping situation. All of that, of course, can be difficult to figure out when do I adhere to these kind of rules when you program the robot. So the way the robot works is that it will automatically adjust any motion by speed scaling to sort of obey all these limits. We have 17 different limits that it continuously monitors. So what happened with the old ROS driver is that what you see on this graph is a motion that was supposed to look like it's a joint position of base joint, I think. And if you look at the sort of cyan graph that goes all the way to close to 2 pi and back, that was how the motion was supposed to look. But because you put a safety speed limit, then the actual motion that the robot did was sort of the purple one, right? And that's okay for many cases. That is how you will experience it when you actually execute the program. So you'll know that that is how it is. So the problem was that ROS had no idea. So the ROS still thought that, or the ROS driver still thought that the robot did the cyan trajectory, meaning that the actual set points ran away from the robot during execution. So we fixed that so that now ROS actually tracks what the robot does. It adheres to the safety compliance and sort of adjusts the motion sequencing that ROS does, making sure that all the trajectories follows, and in the end you will not end in these situations where you get unexpected behavior because the robot targets is somewhere else than the robot actually is. And maybe a lot of you guys have experienced that when working with the robot. So in the end, it's again taking away the things that potentially can lead you guys to spending a lot of time on making stuff work. So on the E-series, we introduced a tool-based communication platform. So on the tool flange of the robot, there's a communication port, and it's not a communication port that is sort of physically directed to some outlet in the control cabinet, as it most often is. It's a tool communication interface that actually enables you guys to put software components in the control system of the robot. We can use it in our UR-CAP environment, so you can actually make a piece of software that runs on the robot controller where you can communicate to whatever end effector you put on the arm. But of course in ROS, you may want to put something at the end of the arm. You probably would like to avoid all the external cables that run down and gets tangled up everywhere. So of course we wanted to provide that service to you guys as well. So what we actually do is we do forward the serial port, the RS-485 serial port that can run up to sort of 5 megabits. We forward that to the ROS machine. So you can actually open it up, connect it as it was sort of a physical serial port on the ROS machine, which allows you to use existing drivers like the Robotics gripper driver. You can actually run the ROS Robotics driver on your ROS PC and actuate the gripper on the robot through this tunnel. And if you want to put an Arduino or whatever you might think of putting at the end effector, you can still communicate and control it directly from your ROS PC, and we would forward all the signals to the end. Yeah, so that is sort of the rough feature set of the new driver. So I think we managed to fix a lot of things that gave you headaches, and at least so much that at least now the sort of previous UR modern driver was declared depreciated, I think a month ago. So we hope at least to get all of you guys transitioning to this driver and also helping us sort of find if we have any remaining issues so we can get all that ironed out now that we are at it. All right, so what's the next steps? So I think we managed to fix a lot of things, but there's still a lot of way to go, I think, until we can sort of really get everything running at a level where we can trust it to be running 24/7 on the factory floors. So we were lucky, and we actually applied for another FTP project in the ROS-I project, and we're really happy to get that granted. So we will be starting sort of the ROS driver 2.0 work and seeing what we can do. In the first round, it was all about cleaning up, improving the performance of what the sort of previous robot driver paradigms was all about. But now let's try to take it to the next level where we can also get a bit closer to industrial grade performance and to a point where we can actually start really putting ROS to the factory floors. So we had some goals around this. So what did we want to do? So it's still about industrial grade performance is about getting the reliability and stability that you would need to running 24/7 factory work, which is something about real-time constraints. You actually want things deterministically to be reacting to certain signals at a point. So it's for some research, you may be okay to live with suboptimal performance, but in the end, if you want it running on the factory floor, you need to use the hardware to its limits. And unfortunately, that's not sort of the case at the moment. So we want to provide easy access to all the control interfaces of the robot. We also really want to exploit sort of the full motion quality and responsiveness to the robot. And in the end now, with the current sort of ROS driver, all the motion interpolation still happens on the ROS machine. It sends targets at a 500 hertz rate, which is nice until you sort of have an Ethernet dropout, or that at least then you will be in suboptimal control in that point in time. And in the end, it also somehow pushes the motion interpolation, the motion quality that we actually have a lot of people that spend a lot of time on making sure is good. It pushes that to a piece of ROS software that is designed in a general manner to support most industrial robots. And I think it's important to, if we want to go to a sort of industrial grade control of robots, then we need in the ROS community to think of interfaces that doesn't force us to go to the lowest common denominator of how we can generalize across all industrial robots. So of course we want to have it still a vendor in sort of vendor independent. We still want the sort of generic interfaces. But in the end, it's also important that we don't end up then having interfaces where we spend a lot of time on trying to get stuff to behave like the robot just would have behaved if you took up the teach pen and used it as any normal user, right? And I've actually heard that a few times. I hear, why is it performing like that? Well, we're using ROS. And it shouldn't be the excuse of saying, okay, my robot is performing poorly, and the reason is that I'm using ROS. That's not really helping the situation of bringing ROS's name to the industrial context, right? Again, we want to do more to also making sure that this sort of integrated and seamless collaboration between ROS and the robot happens. And it, again, also to help us getting a bit closer to the commercial market. So we have seen a ton of research done in the ROS communities that is pretty good, that is actually components that would make a lot of sense to bring to the industrial market, but still doesn't get there because it's sort of a big infrastructural thing that how do you take this one ROS node and get it all the way to the industry? There's a lot of sort of strings attached that it really is difficult to bring out. So we want to make sure that we can make that happen again, right? So first goal is to have just Cartesian control. I mean, that's one of the general paradigms of robot programming in general is that most programs are either sort of halfway made in joint space, which is the current available ROS paradigm, or in Cartesian space, which is often when it comes to the detailed manipulation. And of course, there are toolkits like MoveIt and so on, so you can set up a pipeline for Cartesian control in ROS, but it's not really easy to use. You need to know how to set up the inverse kinematics solvers and all of that. So I think one of the first steps is that we'll bring up a discussion in the ROS community, because Cartesian control is not that easy to define. There's a lot of having the targets is an easy thing, but figuring out how do we control what kind of posture would the robot be in and so on is a generic challenge that all manufacturers have different solutions to. So how do we bring that into a generic ROS interface that sort of solves it all? So we'll bring that in, we'll try to set a standard. We'll definitely want all the feedback is from you guys as a community to how do we fix that and find the right compromise on that. Then we want to bring in, you saw Arne's presentation yesterday on the work that they did at FZI to enable Cartesian control in ROS. So we definitely want to integrate that Cartesian control package into so it really works seamlessly into our ROS driver as well. Then, and the middle point is about seamless switching of execution flow between ROS and the robot. So again, in an actual industrial application, there's a lot of things that really depend on real-time reactiveness. So if you have a contact with a part and really want the robot to react immediately to that, or you're passing something where you actually need to set a sensor, or you want to grip a part really, really fast when you sort of hit a point. Well, if you have to pass control back to ROS, saying, okay, now I arrived at this waypoint, wait until everything sort of propagates to TF, until you start sending a call to activate an IO that toggles a gripper, sending control back, saying, now I'm done, and then start sending a new command to the robot. It simply takes too long time. So if we want to do that in an industrial grade way, then we need to figure out how do we push all this real-time behavior to the robot side, right? And it's the same thing for all of it. And of course, the other thing gives a lot of flexibility. We want to keep that sort of nice and seamless interface. But many times I've seen when people have to try to tackle this problem and in the end have no other way, then they start sort of mutilating the original ROS APIs that we have and figure out tricks on how to do this. And in the end, we want to do it so that you don't have to do that, right? So you actually spend time on doing the actual stuff that you want to do. Yeah, so we really want to look at how can we make this work so we can send all the decisions to the robot controller. We can send, if you're doing a static sequence of motions, then let the robot controller sort of sequence you through all of that. And when you have to do sort of the very hard real-time stuff, or the soft real-time stuff that you want to do on the ROS side, then you can make sure that that happens. And the last thing is we want to investigate, so how can we use ROS as a service more? So can you, like you saw in the video, can you use ROS in different parts of your program? But if you just want ROS as a component that would provide you a pose that the robot should go to for a bin picking, or it should give you the trajectory, how to grip a part inside a bin, but that's pretty much it. Everything else is a static program. Well, then how do you leverage ROS as a service there? How do you acquire, if you work with AI features in ROS and so on, so how do you actually use ROS as a knowledge server and get this sort of seamless integration between the robot and ROS? Yeah, so that's sort of the three main goals that we try to tackle in this. I think this is a bit more around, so how do we, in general, we have this challenge of respecting the real-time barriers. And in any system, there's sort of, at least in any automation and hard real-time system, there's a part that can actually work in hard real-time. Thomas also told us that in KRL, you actually have deterministic execution of hard real-time script. We have the same thing. And as soon as you sort of crosses the barrier into the ROS, then you're at least in a soft real-time paradigm. Right? You may be able to, with the right real-time patches, to make the driver feed set points at a 500 hertz rate. But what happens if you have to make a decision at some point in your program? Well, then you have to ask someone else in the ROS pipeline, right? Either your trajectory generator or your planner or whatever else you have in your stack. What actually means that you're pushing the hard real-time requirement backwards in your chain. And in the end, it will sort of be the lowest common denominator that sets the responsiveness to how fast you can react to things. So in order to somehow make this work, we need to push, at least make the hard real-time layer capable of making the very immediate next step decisions that it needs to make, right? I think that's some of the things that we want to look a bit at. How can we do that? How can we create that proper balance between what's executed in ROS and what's executed in, and there's all benefits of all of it. All right, so of course we also want to bring in some of the new features of the robot, right? So in the end, we keep pushing new features to the robot, and we want to make sure that all that benefit is also provided to the ROS environment. So I think around summer we launched sort of a more reactive programming paradigm in halfway in the CB3 series and fully in the E series, so you can program more reactive-based motions. So we have you can now do any motion until an event occurs. An event could potentially be, you can have a distance sensor, you can have any sort of sensor that will break your motion at any point. In 5.4, we also introduced contact detection as sort of an input sensor for that. So now you can do something like stacking, palletizing, purely based on contacts. You can pretty much do a 3-line program that will allow you to do a cubic palletizing, but just moving down until you have a contact, moving sideways until you have a contact, and then moving sort of into the corner. It will actually allow you to stack parts really tightly. But it's also some of the things that you would need to do stuff like assembly, because in the end, in assembly, you're working with sort of zero tolerances. So you would need something that is very reactive, can do it in hard real time, and this is some of the stuff we can do here in our 2 millisecond hard real-time response rate. So we can pretty much do steel-to-steel contacts in a 100 millimeters per second without really hearing it. It's quite disturbance tolerant, the contact detector, and it can really work on both sort of soft contacts into rubberish stuff, or it can do like hard impacts, like steel-to-steel impacts. And we even sort of detect, if you have a soft contact with a material, then we may move slightly into the material, but we actually do know when the contact started. So we can retract to the exact surface of the part, or you can retract to sort of, let's say, any distance. Either if you want to make sure that you don't clamp the part, you can move up a few millimeters or so. So all that sort of functionality we want to bring into ROS as well. It's really hard to do without having your fingers into the real-time control loop as well. 5 days ago, we also launched a 5.6 software version for the E-Series that came with a dynamic path offset feature. So dynamic path offset is a real-time servoing mode that will allow you to do 6 degrees of freedom adjustment to the robot in real time as well. So you can either do any sort of, you can do any type of motion, have a complete normal UR program running, And then you can do any type of overlay. So if you want to do a seam or sort of a welding seam, you can overlay a very nice sine wave to the motion by just somehow manipulating a TCP offset. If you want to do admittance control while doing fully normal motions, you can also do that dynamically in a concurrent thread. You can also do dynamic path offset respective to the base of the robot. So if you put the base on a mobile robot and you maybe maneuver it into the final position, then you can actually adjust the TCP of the robot to at least be intolerant to whatever motions the mobile robot. Or if you put the robot on a linear axis, either sort of horizontally or vertically, or if you put it on top of another big robot, then you can actually also motion compensate all of that. So of course we want to bring these kind of features into the new driver as well. Yeah, so that's pretty much it. That's the plans for the new driver. So I think one thing is make sure you leverage sort of the new driver, download it, give us all your feedback, and also of course we like every community input. We somehow is a bit solid on what do we want to do with the new driver, but if you have any nuance that we should think of, if you have any ideas of how we can do stuff, then please contact us. If you have a desire also in being in the loop of affecting the definition of a Cartesian interface, let us know. We do have a ross@universalrobots.com email address, so please write to that one. Yeah, it was almost too easy, Thomas, yeah. Mostly for feedback and ideas. So if you have issues, bug report stuff that needs to go concerning the driver, then please use the issue tracker on our GitHub repository. There's actually also a ROS driver forum in our UR Plus forum. So it does need you guys to sign up, but we have a lot of people that already did that. So if you want sort of have a more discussion-based thing, have some help, feedback, work with the community there, then you could go in there and have the discussion there. So use the GitHub for issues, the email for feedback and ideas and more sort of substantial sizes, and use our forums for more open discussions. So thank you.
Thank you, Anders. So we have time for question just before the lunch break. Yeah.
Did you evaluate a micro-ROS in order to connect the robot to ROS-2?
So yeah, as you all noticed, I guess ROS-2 wasn't a part of the talk. And I think actually originally, even with the first driver, we had a strong ambition of saying, okay, I said real time a lot of times here, right? So ROS-2 is the obvious target. I think the challenge is still that ROS control, which is sort of the basis for most of the ROS-Industrial robot drivers, are not ported to ROS-2 yet. So the challenge is still that infrastructure work needed to, and we discussed a lot, should we put that into scope of, but we actually decided to put our resources on sort of fixing the usability part. Everything is designed so it should be easy to port to ROS-2. So right now still the connection between the ROS machine and the robot is using sort of just legacy connections that we do have. I guess potentially you could put micro ROS on the robot Linux machine and then, but you would it wouldn't matter much because you would still be using the legacy interfaces then just on the local part of the robot, right? Of course you could integrate it even further, but at least it's not the scope yet.
Any other question? In the back. Last one.
Hello. Basically, you are saying that like you are planning to use the reactive motion planning, right?
No.
You're one of the presentation. You are telling that reactive motions control.
Yeah.
So means that like it will avoid the collisions objects in the real time, as far as I understand, right?
Yeah, so what we want to bring is at least that we can work reactively on events that happens in the scene, right? So it's not necessarily about if you want to plan a new motion, that's when you get into ROS space. But that's probably some of the stuff that the new driver could do, that you can actually do a very nice motion, even just a linear motion that you let the robot interpolate. And then at some point, if you have an event either physically detected at the robot or happening at the ROS side, you should be able to very seamlessly switch into a control mode where you can write the motion planner and you can navigate around a part, an obstacle, whatever you want, and probably go back and resume your very nice linear motion that the robot was interpolating. So we want to make sure that we somehow keep giving you the power of doing that, but still keeping us in control and making the good motion performance that we can do on sort of all the basic stuff that a robot normally does.